Okay, it is 2:30, so I will begin this harebrained presentation idea I had, which is a little bit more, a little bit more complicated, a little bit more ambitious than I originally thought it was going to be with all the stuff I brought, but that's, how it goes sometimes. So I'm going to go ahead and start. My name is Nate Lockhart, and this is Fun with Hardware Logic. So this is a DIY TTL electronics primer. So we're not talking about code, we're talking about digital logic on a very base level. What I really want to do with this is start to demystify a lot of these things for you guys. Because you can kind of see, you see something like this, and if you don't know anything about electronics, this is like gobbledygook, what is this? But I want to take away a lot of that just to see it's really not as complicated as it might appear on first glance. And it's fun. And Kevin's bringing me my little tiny speaker doodad. Thanks so much. Oh, sick. And that's a nice shielded one. Boy, howdy. Thank you, buddy. Does it still work? Yeah. I 3D printed this little guy so I could use it for sound testing. Okay, there we go. So yes, fun with hardware logic. Let's go down to the next slide. Hi, I'm Nate Lockhart. I am a compulsive tinkerer. I'm a very infrequent podcaster. I think I did 2 episodes of my podcast last year. I have 2 young kids, and my wife got a big new job. And then I started my own small business at the same time. So it's a beautiful disaster. Don't recommend doing all those things at once, but here we are. My little business is Lockhart Electronics. I repair and modify vintage electronics for a living. It's a lot of fun. I didn't realize that there was that much demand for that kind of work. I've been able to fix things from 50s console stereos to, what else did I work on? I replaced a USB-C port on a tablet, and Steve Lynn, if anybody knows that name, he commissioned me to make a go-between board so he could play Street Fighter the movie, the game, on his Street Fighter 2 cabinet. And he was like, could you do this? And I was like, I guess. And then I did it. And it was fun. So I get to do a lot of neat stuff. And I'm originally from Rochester, New York, as the locals call it. But I'm currently living in Buffalo. And so first things first, what are we talking about here? When we're talking about hardware logic, TTL, what does that even mean? First off, TTL, I use it as a catch-all term for this sort of hardware experimentation. TTL stands for transistor logic. It's not important to know that for what we're going to do right here today. So don't get hung up on that, what do you call it? Those initials. CMOS, the TTL, CMOS, there's DTL logic, RTL logic, if you really want to go back. The original Odyssey is DTL logic, diode transistor. It's very fun to work on those things. The guy who engineered the design for that product, for the Odyssey as a product, really had engineers in mind because everything is on nice, neat little cards that you can pull out. It's so nice. Kudos to that guy. Anyways, so with the logic that we're talking about here, this is binary logic, on or off, 1, 0. In the case of what we're using here today, and what was most common for a very long time, is 0 volts, ground is off or 0, 5 volts is 1 on, high. Sometimes you'll see it referred to high or low. And today you see a lot more 3.3 volt logic. Being that most of my stuff is vintage, I don't tend to delve into the 3.3 volt world unless under duress, by having to use a Raspberry Pi Pico or something, or some microcontroller or something like that. I prefer to use the individual logic chips. That's more fun. And there's a lot of different ways to implement that logic, like we talked about, CMOS, DTL, RTL, all that. The way we're going to see it today is in integrated circuits in these little chips that kind of have all these functions built in on the pin level. And these are very simple building blocks that can be built up and cascaded into all sorts of crazy, wonderful things, like computers. In the early 70s, mini computers, those were done with TTL logic or DTL or RTL. The picture there that I have is of a Data General Nova, which was a very popular computer in the early 70s. And when they say the CPU of those machines, what it is it's not a chip, it's a whole board with all the logic of a CPU on individual chips that do each logic function. You also saw it in a lot of early synths. I'm thinking of RMI did a lot with that. They were Rocky Mountain something or other. But the keyboard computer was their big thing. They did digital synth implementations. There's lots of different various single-purpose devices. There were magazines in the 60s and 70s and into the 80s, and even a little bit into the early 90s. Magazines like Radio Electronics or Popular Electronics, and they all had these like DIY, here's what you could do at home in your own lab, and they would give you the schematics and things. So like, here's how you make a door detector, or here's how you make a burglar alarm, or here's a digital tuner for your CB radio that we all have, and because it was the 70s. And there's all sorts of fun stuff. It's really fun to look through those old magazines and see what people were up to and what they were tinkering with. World Radio History, that website, I believe, just has the whole run of it. You can just browse through and look at it. It's fun. Okay. But why though? Why would anyone bother with this? This is old stuff. It's a lot easier to do FPGA or microcontroller programming or whatever have you, because you could just do it all right here on the computer and just do it. You just do the thing. But I find a lot of value in it personally. One is that hands-on experience. When you're programming or something, you're just sort of all typing it in, and then the computer does it all. But with this, it's like programming by hand. It's sort of like where it's like a mix of like arts and crafts, and that's really fun. I really enjoy that aspect of it. It's obviously great to repair old electronics and things like that, to know how these things work and what to expect out of them and all that kind of fun stuff. Like I said, it's a very tactile way to learn these sorts of things. I think that's very valuable, especially if you're getting into programming, to learn how does a computer think on its most base metal level, and that is legitimately on or off. That's the basis of all of this crap. That's what this is built entirely off of. At the very base level, its very soul is on and off. Everything else is built up from that. Yeah, they're fun. It's really fun to mess with this stuff. It's fun to put little wires together and put a couple little buttons, and you turn it on and a little light blinks, and that's cool. And they're like little logic Legos, and you can take different functions and build them up and do all sorts of crazy stuff. I mean, people have created in them, recently, full computers that are TTL. The one I love is called the Minimal 64. It's really neat. It could do quite a lot. The thing I'm trying to do with the Minimal right now is currently it only outputs on VGA, but I want to have it output on composite video, because it only does black and white. But if you get it in composite, you can trick American composite into displaying color when it shouldn't, because of how NTSC television is so weird, because it should be 60 hertz. Everything's 60 hertz. But in order to accommodate the color burst and still make it compatible with black and white sets, the frequency is 59.97. And that really screws with things, but you can play with it. And if you put little tiny black and white lines really close together, the NTSC signal can't tell the difference, and it just kind of says like, I don't know, purple, and it makes like a block of purple. It's super cool. That's how the Apple II does color. That is exactly how the Apple II does color. It's just trickery. It's really a black and white image that they have tricked a television into making color instead. The TRS-80 color computer does it. There's a couple of others, but they're not coming to mind right now. But yeah, it's a lot of fun. So with that all having been said, let's start at the very bottom. This is a NAND gate, okay? That's what we have right there. So we have the chip right there. We have a couple buttons. And I have here, there's a couple little resistors which pull the inputs low. Now, what am I talking about when I say inputs? Let me see. Can you see my mouse cursor? Is my mouse cursor visible to you all? Okay. All right. So the things you need right off the bat with whenever you get any of these little chips, it's good to know the pinout and the truth table. Pinout, truth table. So that way you know what each pin does. Ideally, you have the whole data sheet, which in most cases are very easy to find. Texas Instruments just has them all up there for you to download freely. They're not hard to find at all. Anyway, so you can see here, with this particular chip, this is the ubiquitous 7400. It has 1, 2, 3, 4 NAND gates. And you know, why do I say NAND? It's because it's an inverted AND, meaning that when both inputs are high, the output is low. Otherwise, it's high. And we have 1, 2, 3, 4 of those gates doing exactly that work. And that is how I have it wired here. Ideally, all the unused inputs would be tied low, so that way there's not any little bits of noise, but we'll get to that when we come to it. You don't worry about that now. We're focusing on the gate. And I'm going to plug this sucker in, and you'll see it in action. And if anybody would like to, you may come up and push the buttons because it's fun. You want to come up and demonstrate for us? Thank you so much. So we're going to do this here. I'm going to do this. I'm going to hook it up. I'm going to make sure that I don't, okay. I'm good. Now I'm going to plug it in. So I got my power supply over here, which is way overkill for what we're using it for. These things take up, I would say, this whole circuit is probably 7 milliamps. It's not much. 10 milliamps maybe. So we're going to do that there. Oh, wait. No, this there. Whew, thank you. I got that all mixed up. Got the positive there. Where's my negative? Here we are. Then we'll get the negative to go over here. So you'll see it in action. Now, we're going to turn it on. And you'll see that there is no light currently because they're not on. If you would kindly please press one of the buttons over here. Over this. Yeah, this one. Yep. Nothing. And you do the other one? Nothing. How about both at the same time? There we go. Hooray. Look at that. It turns on. Neat. So cool. Thank you so much. I appreciate your assistance. Does anybody else like to try the OR gate? Do I have any volunteers for the OR gate who like to push some buttons? There you go. Let's push some buttons. Thank you very much. Make sure I get this part over here. So we're going to put it over here. And just a second. Actually, you know what? I need to explain it first. So that was our AND gate. We're going down to the NOR gate. Again, NOR and inverted OR. But that means that either of these inputs being high makes the output low. Otherwise, it's high. So if you would please push any one of those buttons, and it should just turn, other one, there we go. Yeah, there it is, look at that. You can see he's pushing the buttons. If you just move it over here a little bit, there he is. Push the buttons and both will do it. And if he does both at the same time, they'll just be high. And there it is. That's a NOR gate. So you can kind of see just through that it's, that's really all it is. I really want to demystify this stuff because when you see that chip, it really does look intimidating. You're like, how am I supposed to make sense of this? But it really is simply that. And you'll see here that I have, all these little wires here that are hooked up that's just connecting points to points. A few notes when you're messing around with some of this stuff, make sure your voltages are hooked up. We got to make sure that the chip itself gets voltages. So the chip itself needs 5 volts and ground. They're normally on pins, usually the top right pin is the 5 volts and the lower left pin is ground. It's not always that way. A reminder to check your data sheets. I believe the 7476 is a pain in the butt because it uses like the middle and I always get it wrong, which is not fun. And you'll notice, I don't know how well you can tell here, but these things have little notches on them. Up here, you'll see here there's like a little dot. And on a physical chip, there's a little U-shaped notch that you'll see often right here. And that will tell you the orientation of the chip. So you're, you don't flip it around, put it the wrong way, that kind of stuff. Some of these chips are quite resilient. I think the LS series could take a bit of punishment. Lord knows I've done that. Like put the chips in backwards, and then you're like, why does something smell? And it's because like, oh yeah, and then it still worked because they're strong little suckers. It's nice when you could put like a reverse voltage in something and still have it work. It's not always a given. I've actually never put a polarized capacitor in backwards. I've never done that in my whole life, which I'm very proud of. I have, however, been shocked multiple times by 110 volts from the wall, so, it's a trade-off, I guess. It's fine, it's not that bad. You just taste metal for a little bit. Let's see. So yeah, definitely pay attention to chip orientation, and watch out for signal noise, which can be a bit of a problem, especially as your circuits get bigger. The different lines can kind of affect each other. So it's good to have a nice, strong ground plane. And I learned that the hard way because I made a circuit board, my very first circuit board I made, I did not do a ground plane on any of it. And I didn't know why it didn't work. It's a great way to learn this stuff because then you learn why it's important. And I value that, I really do. But now that you're here, I can tell you so you don't have to, waste money getting boards manufactured in China and then wait for them a week and then be disappointed when it doesn't work. And in my case here, we have pull-down resistors. You might be able to see these little guys right there. If we show it, I don't know how well focused that is. I can't tell from here. But we have little resistors there, and those hold the input signals, in this case, hold the input signals to ground. The buttons will send a high voltage or 5 volt signal to the inputs. So we don't want it to be directly connected to ground because if I send 5 volts to the input that's connected to ground, then it's going to short, and that's bad because then it just a bunch of energy just gets dumped into the ground. You don't want to do that, but a resistor keeps the current from getting to be too much. And it's usually a good practice when you're not connecting chips directly to other chips. When you're connecting chips directly to other chips, you don't have to worry about it. It's not a thing. But in this case, where we're using an outside input to trigger the 5 volts, pull-down resistors, pull-up resistors, whatever it normally needs to be. If it normally needs to be high, pull up. If it normally needs to be low, pull down. There you go. So let's see, did I cover everything there? I did. This is a very fun one. Do you need a question of clarification?
On the pull-down resistor.
Yes.
My understanding is when you have pull-up
Basically all you're doing with these resistors, whether they're pulling up, pulling down, they're keeping it from the circuit from short circuiting when you apply 5 volts or 0 volts to it. It's just sort of a protection thing. And pull up or pull down basically is just saying, like, are you holding the signal high to wait for it to get pulled low, or is it normally low and you're waiting for it to get pulled high, you know? And it's holding it down so that way it doesn't touch and then everything short circuits. I don't know if I explained that very well. I'm trying.
I think the idea is you just have to have something between your load.
Yes, that's exactly it. You just need to have something to hold it back. And in our case here, you know, 1K, 2K, the value hardly matters much unless like you're really going for speed, which I hardly ever do. I don't need to for my stuff. That's sort of the idea. Do we have another question or clarification? Because we have bigger questions. I want to save them for the end, but go ahead. Yeah.
Yeah, so the 5 volts in these logic gates, is that like a hard cutoff, or is there like any robustness to
That's a good question. Can I save that for later, afterwards? Sure. Yeah. Because that is a very good question. Actually, you know what? Let's go into it, because this is a good place to do it. I think that was a good question for right here. There is a cutoff, and the data sheets will tell you what that is. Usually, it depends on the logic family, right? If you're using straight TTL, it's not going to budge from low to high until it hits like 4.75 volts. CMOS only needs 2.5 volts from 0 to 5, and it'll take the hint to change. And that can really get you into trouble if you are having circuits that rely on timing. Because if you have the wrong logic family in the wrong place, it might go too soon or it might change over too late. And that can be a big pain in the butt. However, if you're just starting out, I would encourage you to focus on circuits that don't really need to rely on that so much, so you can just really get the concepts down. Because that's sort of like a little bit more, I don't want to say more advanced, but it's something, you know, that happens with more complex circuits that you have to consider. But that's a good point. So that's a very good point. This is one of my favorite circuits because it's essentially 1-bit RAM, which I think is pretty cool. Pull that over. Oops. Oh boy. Having fun here. Let's make sure I put the right stuff in here. That's good. Nothing's getting shorted out. Terrific. There we go. You can see all that, right? All right. So the flip-flop circuit, that's a cute little name. What it is, it's essentially a rudimentary form of digital memory. Here's the pinout and the logic symbol. It probably looks a little bit more complicated than the NOR and NAND gates that we were looking at earlier. What we have here is, I gotta look a little closer, my tired eyes. We got a reset pin, which basically will, you pull that low. I don't know if you guys, how well you can see that, but there's a little line over the reset name. And that means that it is active when it's low. If you don't see that, that means it's active when it's high. So line above, active, low. No line, active, high. So in our case, I don't want the reset. I don't want it to keep trying to reset when I'm trying to do something with it, so we hold it high. We don't need to worry about setting it, so I hold it high. D is the input, whether it's high or low, and then there's a clock. So that tells it to read it, basically. So whatever comes into D, when the clock goes high, it'll read what's at D, whether that's low or high. In this case, I've connected, we have two outputs too, which is kind of neat. There's an output that's Q, right? That's your normal output. And you also have not Q, so the opposite. So you have both in case, you might need, one Boolean truth over the other. And in this case, I wired not Q back to D. So the not Q is wired back to D so that every time I hit a clock pulse, it'll read whatever it isn't and it'll flip-flop between the two. Thus, flip-flop. And so, does someone else want to push buttons and demonstrate? Anybody? Or shall I? Yeah, sure. You want to do it again? Go for it. I'm not going to deny anybody here. Just this one little button here. Just that one, push there. And you'll see that it'll go to the other because it keeps flipping back and forth. If it'll read it, there it goes. It's a little finicky because I don't have a debounce circuit in here, which would make it perfect, but it doesn't, and that's fine. It proves the point. Thank you very much. And there you go. So yeah, you kind of get a 1-bit memory out of it, and I don't know. There's something kind of neat to be able to play with RAM at this tiny of a level. You can't do much with this just as it is, but it's neat to be able to sort of take a microscope to the things that we use every day and see that this is really what it is. It's very basic, base level. And you'll see here too that we have 14 pins here, and that means we have 2 of these flip-flop circuits. So really, it's 2-bit memory, which is pretty cool. You can count up to 4 with that. And this is our truth table here, which gets more important with the more complex chips that you use. It tells you what will happen if the preset, or which is the reset, is high or low, what happens with the clock pulses, what happens when D is there, and all that kind of stuff. This will tell you everything you need to know. So again, the data sheets will tell you everything. You won't need to go about it blindly. Pardon me. Excuse me. Another fun thing you can do is using things with a clock. So up to this point, we've been triggering the states and showing the things with pushes of a button outside. Having a clock means that you can set it off on its own. There are lots of different ways to have a clock. You could just do like a crystal, right? Like an oscillator. There's lots of different values that you can do for that. Some people like to use the 555 timer. Anybody familiar with the 555? Yeah, there we go. We got a few people who know what I'm talking about. 555 timers are fun. You get to mess with stuff. You get to make blinky lights and who knows what else. When I make clocks, I prefer to use the LM567, which is a similar package size, so it's 8 pins. But you can make a clock with far less components than you can with the 555, which I really appreciate, and it's a lot more stable because it's mainly used as a tone detector, which is kind of fun. People used to use that for phone freaking back in the day, if anybody knows what that is. Yeah, so you could get free calls on payphones. Real important stuff. Let's see, I'll show you here the clock. So yeah, you could do that. Actually, I was building a thing for a while, just kind of for fun to see if I could. I wanted to build a totally hardware-based tape data storage thing because it could tell like high and low or the frequencies of the sound that you're putting into it and then decide whether it counts as a high or a low, and I thought that'd be kind of fun. And then I lost like a week doing that, and then, yes, do you have a question of clarification?
I might be a little too advanced. How is the clock signal to 5 in the 5, 6, 7? Is it resistance based similar to 5, 5?
Yes, yeah. In fact, I'll bring it right up because I have one right here that we could take a look at. I'm glad you asked. There it is. Look at that guy. Did I do it? There it is. Okay. So there's our little 555 timer, and It just has a couple resistors and a capacitor, and that's what determines the timing. You play with, I believe, what's the formula for it? 1 RC over C? I don't know. It's in the data sheet. But messing with those values, you can speed down or slow up the, slow down, speed up. There it is. Slow down or speed up the rate of oscillation. So let's put this in here. And for right now, we're not really going to hear anything out of it. That's ground. Good. There we go. And thank you for bearing with me. There's that. It's not doing anything that you could see right now. I'll move it over in a bit and you will see what it's doing. But it's basically spitting out. In fact, let's turn it on here to the oscilloscope so we can kind of see what's going on. What's going on? Set the ground. And we'll see what we're getting out of the output. Right here. You see it? Yeah. So let's adjust it so we can see a little bit better. Nope, we don't want that. No, we don't want that. Oh, it's adjusting that. Okay. There we go. We got that, and then we need to see it up close. There it is. And you can see it going. Up and down a bunch. That's all it's doing. And in this case, it is doing it at the rate of, can't read it. Anyway, trust me, it's going at some sort of rate. Yeah. Oh, there it is, 62.89 hertz. So we have that. That's making us a nice, reliable little clock. You can do fun things with clocks. We can plug them into counters, which is pretty fun. In this case, there's a lot of different counting chips for if you're going to mess with this sort of stuff. Some of them count, like in decades, right? Like base 10, but they do it binary base 10. They just flip over when they hit 9 instead of hitting 16, right? Most of them are 4-bit binary, counting up to 16. There are some that do 8-bit binary. I don't think many of them do more than that, but you can build them off of each other. So you might just only have like one 4-bit chip, but then that chip will have a little carryover bit that you can use to cascade into another counter, which will count when you hit the full count of that one. So you can kind of keep building up, and you could, I don't know, have like a 128-bit counter. I mean, it would be big, it would take up a lot of space, but hey, go nuts, that's what it's all for. We can see the nice pinouts here, and it'll tell us what happens when we do what. There's a reset mode, a load mode. In this case, I like to use the 74161, which is just, counts up to 16 in binary, up to 1111, and then it goes back again. But you can also preload it, which is kind of fun. So if you wanted to start counting from something else, you can set a preload into it, and it'll start counting from there. There are other counters too that instead of just going one way, you could do both ways. You can go up or down instead of just up. But in this case, I like to use the 74161. It's very reliable and has a lot of features in a very small package. That's what I like. In this case, I have it counting, and I put 2 of them together so we could get full 8-bit counting. If you can see it. Is it working? Nope. It's because it fell out. What happened? Go. There it is. Hooray. It's counting up very fast. There's another fun thing you can do with all of these frequencies, because we're making frequencies, right? Like, we're not just counting. We're dividing that clock into longer, slower and slower frequencies, because we have access to every single output pin there, right? Because it's all binary, and they're flashing at different times. meaning that we just sort of created a little way to get different divisions of that clock just in case we need to do something a little wild or different. So what I could show you here, in this case, because this is a pretty fun thing to do, it's not going to sound super pleasant, but it's all right. This thing can only put out a 1/4 watt of sound, so unless I put it up to the microphone, but I won't do that to you people. So I have here my little speaker. This is a little guy just used for testing. It's nice to have. I just threw it together real quick in Fusion and made it. And then I have it connect to a little wire. I have the outputs here. I made ground black so I wouldn't forget. Let's hook up that guy. So that's connected. Not very well, but it doesn't matter. We'll make sure that's connected to there. And then we have 2 other outputs, and we could just connect this to whatever. And this gives me access to the signal on the cable. I could also even just hook it up right to the plug itself if I wanted to. It's not strictly necessary to do it this way. I just like to do it that way. And now where are my little jumper cables? Did I put them over here? Little jumper cables. I think I put them... There they are. 'Cause I don't know about you, but it's a great place to keep them. You know, right in your jacket pocket. That makes sense to me anyways. I don't know. Okay, so let's get this up here. We're going to connect this one part to ground so it has some way to complete a circuit. There's that. And we're going to hook up another one to some of the different signals in here. So let's give that a little peek and see if any of these things sound like anything. Here we are. These things might come loose in a little bit because the grip on these things is a little tenuous, but we'll figure it out. It's good. Everything's good. Everybody's happy. Everyone's having a great time. Okay, so let's turn this guy on. There he is, and I'm going to put it up here, and you'll probably hear a little bit of noise. I don't think we're hearing anything there because the pitch is too high. Let's hear it down here. Where did I lose it already? Do it for me, buddy. Sorry. Oh. It's a little low, but you can kind of hear it. Can you guys hear that?
Yes.
Yeah. We get a higher pitch too. You can. Why is this not connected? I'm not seeming to be getting a good connection. But you can trust me on this. It does do this, if I can get it to freaking work. Hold on, I'm going to try one more thing. Yeah, I'm not quite getting it, which I think is just not quite making a good connection into what I'm trying to do here. Yeah, I don't know what's happening. Oh, there it is. You hear that?
Yeah.
It's doing that. Or we do it over here. Hey, there it is. Thank you. And we get the different frequencies. So you go.
What was that? What input were you using for that last one?
That's the highest one. So that was the highest one.
The highest bits?
The least significant bit, which is the one that's going the fastest. That's the first digit. Yeah. That's a very low pitch, obviously. And you can change the frequency. That's delicious. Great. Beautiful music. I did it. Thank you for your support and encouragement. Yes, they are. They are. They can go awry very easily, and I appreciate your patience. Least significant bit? Okay, yeah. It's the one that sounds the most pleasant. I mean, you can play with the timing again by just changing the value of the capacitor or the resistors, and you can get all sorts of different pitches and all these sorts of fun things. And I mean, this is like, you could probably make it a little bit more stable using different kinds of components. And in fact, I did do that for my brother for his birthday one year. He's a big experimental music guy. And he, so I made for him an organ out of a bunch of these chips, more finely tuned with more stable capacitance and things like that. So that way he could adjust the tone of each of the 12 tones in the scale and hook them up. And I had them into counters so that way you'd get different octaves of the same note. And you could do like little circuits in between to bend with the sound and all this kind of fun stuff. But yeah, I mean, that's just, there you go, you just saw it there. Another fun thing you could do is to put them all together. I brought this with me. This is a board, a video board that I designed based off of an old book from the 70s called How to Design and Build Your Own Custom TV Games by a guy named David L. Heiserman. He taught at the Ohio State University. He passed away the same year, like a few months before I started this project. So it's kind of a bummer. But it was a really fun way to learn electronics. It really was what pushed me into it. And I really brute forced my way into doing it. But this board uses a lot of the concepts that we've just seen. It uses flip-flops, it uses counters, it uses AND gates, OR gates, you know, and the fun thing with the AND gates is it doesn't just have to be like 1, 2 inputs. You could do 3 input ANDs, you could do 4 input NANDs, you could do 8 input NANDs. You know, you could do all of that, and that's all represented here on this board. And what's fun is when you get the counters to count to the same frequency as the North American television standard. Because you can do that, and you can make it count all the way across and all the way down in the same frequency that a CRT is expecting. And with that, we could do some neat things with it. So let me grab a breadboard over here. I'm going to take this, and I'm going to turn on this television, or broadcast monitor. Okay. So with this, I need to get, this thing has an output. So what we have here, I'll put it up here so we can all see it. I'll unplug this for now. What you can, I don't know how well it is to see, how good you can see it, but all those are labeled. All those inputs. That's how we communicate with this board. And I don't know if you can see it very well, but there are different divisions, clock divisions of those horizontal and vertical frequencies, and we can put them into the video data input to produce rudimentary pictures. So, we'll do that. Let's unplug over here. We don't need this to count anymore, thank you. Where's my other one? Here it is. We don't need this. And we don't need this. Okay. Let's get over here. And when I initially put on the power, you're not going to see anything right away because there's nothing going into the video data. The video data goes in on a certain pin. If I can find my things. Here we go. Let's put you over here. Again, thank you for your patience. Oops. So we're going to plug that in there. And then we're going to take a certain division of one of these frequencies that I have listed out. So it's counting all across the screen 455 times. Then when it hits 455, it restarts. There's another counter that's counting how many times it's counting to 455. That counter goes to 262. And then once it hits 262, it resets. And it does this over and over and over and over again. So we're going to find a different thing here. Sure. One of them, the horizontal frequency is 455. So it counts to 455. There's another counter keeping track of how many times it counts to 455. And that's the vertical counter, which counts to 262. That's the beauty of North American television. Yeah. So these are vertical lines, or at least they should be. Do we see anything? Oh, I bet the brightness is down. Come on now. Bring it on. Did I plug it into the wrong one? Oh! I didn't hook up the power. Listen. Yeah. I didn't even turn it on to begin with. This is the fun thing, you know. You do this, and then it turns out that. How about that? You getting anything? Right. Almost. No, that's not it. Oops. That's what I wanted to do. Come on now, you can do it. I know you can. Oh. Yeah. Let's see. The horizontal frequency seems to be off. Let's see.
Can I point a webcam at it from the back?
Yes. Here, let's. I don't know why it's doing that. It shouldn't be. Let's see. Oh, is this it? Nope. That's not right. Why are you doing that, sir? Oh, that's more like it. I had it in the wrong pen. Oh, boy. Let me just have fun. There it is. That's what you should be seeing. That's what you should be seeing. Let me see if we can prop this up so people can see it better. Don't look, you're going to get dizzy. Look at that. And you get to see a little bit of the raster scan because it's not quite in sync. But yeah, that's basically what we're doing here. And I can change the, oh, thank you. It took a very long time to get this to do this. A lot of it is because in that book that I mentioned earlier, How to Design and Build Your Own Custom TV Games by David L. Heiserman, printed in 1978, there is an error in almost every single one of the schematics. And I will tell you, though, that was also a very good way to learn electronics, because I had to learn what was wrong and why it was wrong. And yeah, I could change the frequencies here. Let's do, I don't know, this. There you go. Now it's vertical lines instead. So we're going into different divisions of the raster. So that's, yeah. Is that vertical? That's horizontal. That's horizontal, yeah. You can go to like something as crazy as like, I don't know, this, and you can get, like for you probably can't even see the difference, but it is a bunch of tiny little lines. There you go, there's some there. And yeah, that is what I spent a lot of my time doing. And you can do all sorts of things with all these little logic gates. You can make them, I mean, if you can make a TV raster out of them, what can't you do? So if you're going to be doing this yourself, I'm going to wrap up because I know my time is very limited, and I want to make sure I leave at least a little time for questions. It's okay to mess up. If you go into this, seriously, it's okay. You don't have to know everything right away. You can screw it up. You can burn a chip. You can, I don't know, shock yourself. It's fine. Like, you'll learn. And there's lots of people you can come to talk to me. I'll happily answer questions judgment-free. Everybody has to start somewhere. And if you get stumped, you know, it's okay. Like, one of my favorite YouTube series is Adrian's Digital Basement. I don't know if any of you people are familiar, but the thing I love most about him is he is not shy about when things don't go right. And, you know, what does he do? He takes a break. He takes a walk. He eats dinner, you know? And I'm so grateful that he shows that part of the process, and that, like, even though him, who has done so many repairs, he still gets hit with, you know, something that stumps him, and it's okay because he does get through it. And yeah, that's what I want you all to know. Anyways, thank you very much. I want to get right to the questions because I don't want to, you know, I really don't want to run over. Thank you very much. So these are my links and all that kind of fun jazz. My Lockhart Electronics currently doesn't go anywhere. I just started it, but, you know, maybe like check back in like a week. I think my Facebook page at least is up for Lockhart Electronics. You can bug me there too. This is all my stuff. The board design for this video board is on my GitHub. If for whatever reason you want to have some manufactured and, you know, go to town, please. I want more hardware weirdos out there. You know, join me in my madness. And yeah, so that would do it. Thank you very much. Do we have any questions? We're going to start right here in the front. Mm-hmm.
Have you ever built a bucket brigade circuit before?
A bucket, they're asking if I have built a bucket brigade circuit. I have not. I'm not sure what that is, but I'm curious. That's for sure. Pink hat, yeah.
If you're starting from scratch, say you have barely any hardware, any
Uh-huh.
peripherals, anything like that, and you're trying to get a computer to start on this sort of thing, in your opinion, where is it okay to go cheap and where should you not go cheap?
Go cheap. That's a great question. Do not cheap out on breadboards. Don't do that because they get really flaky, and I would build a circuit and be like, why doesn't it work? Oh, it's because the contacts on this are terrible and they're flaky, and if I hold the wires just like this, then it works. And no. The brand you want, the brand that I trust, Busboard. That's right. Yep. That's the one I swear by. Oh, did it go out? Yeah, because I brought it up. It doesn't matter.
There's a guy that did a whole survey.
Yeah, Busboard's the one I swear by. Do that. It'll be great. Cheaping out on other things, like if you're just experimenting, it doesn't matter for the rest of the stuff. Like if you're just experimenting, having fun, don't worry about getting the good stuff. I mean, later on, like when you're really like making something because you've nailed down what you want to do, then I would try to get quality components. But until then, I wouldn't. Like for this video board that I built, like I made sure to put in like Nichicon caps, you know, and the good stuff, and not like the weirdo like Chong X brand, whatever. Yeah, that's a good question. Thank you. No, you don't need to do that. You don't need the Rigol oscilloscope right away. This is a very nice oscilloscope that I have here. It's 4-channel. It can go up to, I think, it's got quite a frequency range. But you don't need to do that. They have oscilloscopes you can get that will be just fine for $50. You know, and a multimeter, that's a good thing to have. I have mine with me. Yeah, thank you. Any other questions? I'm trying to go back. Let's go black hoodie there. Yes.
So I feel like for you, when you're doing this and getting into it,
Uh-huh.
and what was the point where you were like, oh, I can make a business out of this? It's small
Oh.
business, like where you forgot this like a band. Here's how that started.
So he's asking me how I got started with my business and how it went from a hobby to, you know, trying to make it an income. And the answer was, it was a lot of, I needed a lot of encouragement from my wife, my partner, because I would do this stuff and I started fixing things for people. Like I started really getting into this about like 6 or 7 years ago. And I just sort of kept building up skills as I kept taking bigger risks and all this kind of thing. And it was very hard for me to want to go into business because I just thought, well, if I can do it, can anybody? Like, so that, and then like, just really devaluing my own skills. And my wife is the one who was like, no, not everybody can do it. And even if everybody could do it, not everybody wants to do it. So put yourself out there. So I am. Yeah, it took a long time, but I did get there, and I do it now, and it's really fun. So thank you. That's a good question. I think we have time for a couple more. Oh, way up front here, yes?
Yeah, so if you're just starting out, what are some good resources to learn from?
I think that's an excellent question. He's asking if you just starting out with the electronics and all this hobby stuff, where do you start? And there are a couple things that I always tell people. One is there's a book from the Make magazine people called More Electronics. And it is a very no-nonsense beginner's book. It doesn't wade in jargon. It just puts it out there in simple terms without being condescending, and I think that's terrific. More Electronics is the name of that book. And the other thing I recommend is watching Adrian's Digital Basement. And it's not so much because of the technical expertise, but because of the attitude that he has on display, and I think that is an excellent attitude for learning and for being kind to yourself while you're learning. And I think that's very, very, very important. Thank you. It's a great question. Do we have any others? I think I have time for, maybe. Red bandana? Yeah.
Do you have any particular like tools or techniques you use for diagramming the circuits to start putting these components together?
Like drawing schematics? Is that what you're asking? So he's asking about like what sort of diagrams do you go by to learn these sorts of things. And when you start at the very beginner level, they'll show you like exactly where on a breadboard to put something. That's something I did not explain earlier, and I really should have, is that on this breadboard, you'll see that there are rows and columns. All along this way, those holes are all connected to each other. Not this way, but this way. So you can connect things along there in series with that. And those books will really go into, and then later on you'll see schematics. And those schematics will use symbols and things like that instead of like pictures of breadboards with lines drawn where to put things. But they really build up, and the book that I mentioned earlier, I think really does a good job of that. So, yes, another question. I just want to see who else has a hand up. Is there anything? Blue shirt. Yes.
You mentioned that schematics and data sets are easy to get from 70s and 80s things, but are those digital resources, or are you having to go to?
They are indeed digital resources. He's asking where you get these materials to like these schematics and things like that, especially with the 70s stuff. And yes, it's all digital. Like radio electronics is all online. The Internet Archive has them for you to borrow digitally. The World Radio History Foundation just has them for you to download if you want them. There's one that there's a circuit I'm really intrigued by, and it is copying your Atari game cartridges to tape cassette and then loading them again off of tape. And I'm just like, I want to build that so bad. I have no time to do that, but I want it to do it so bad. Somebody hire me to make that, please. Yes. Oh, what's that? Because it's cool. Yeah. It's tape. They save data on. You know what tapes are? Tapes are thin strips of plastic with rust on it, and it saves stuff. That's so cool. Like, I can't believe that works. I love this old stuff. The whole Imagination through limitation is a big part of it, and I like that a lot. We are at 3:30. I'll be around if anybody wants to chat about stuff, but thank you so much, everybody, for coming. I'm very grateful that you all took your time to be here.